going back to the beginning of the 20th century, how do you imagine space-time? How do we as human beings supposed to visualize and think about space-time
Mm.
where, time is just another dimension in this 4D space
Mm.
that combines space and time? Because we've been talking about morphing in all kinds of different ways, the curvature of space-time. Like, how are we supposed to conceive of it? How do you think of it?
Yeah.
Time is just another dimension.
There are different ways we can think about it. We can imagine drawing a map of space and treating time as another direction in that map. But we're limited because as three-dimensional beings, we can't really draw 4 dimensions, which is what I'd require. 3 spatial, because I'm pretty sure there's at least 3. I think there's probably more. But I'm happy just talking about the large dimensions, the 3 we see up, down, right? East, west, north, south, three spatial dimensions. And time is the 4th. Nobody can really visualize it. But we know mathematically how to unpack it on paper. I can mathematically suppress one of the spatial dimensions, and then I can draw it pretty well. Now, the problem is that we'd call it a Euclidean spacetime. A Euclidean spacetime is when all the dimensions are orthogonal and are treated equally. Time is not another Euclidean dimension. It's actually a Minkowskian spacetime. But it means that the spacetime, we're misrepresenting it when we draw it, but we're misrepresenting it in a way that we deeply understand. I can give you an example. The Earth, I can project onto a flat sheet of paper. I am now misrepresenting a map of the Earth. And I know that, but I understand the rules for how to add distances on this misrepresentation because the Earth is not a flat sheet of paper. It's a sphere. And as long as I understand the rules for how I get from the North Pole to the South Pole, that I'm moving along really a great arc, and I understand that the distance is not the distance I would measure on a flat sheet of paper, then I can do a really great job with a map and understanding the rules of addition, multiplication, and the geometries, not the geometry of a flat sheet of paper. I can do the same thing with spacetime. I can draw it on a flat sheet of paper, but I know that it's not actually a flat Euclidean space. And so my rules for measuring distances are different than the rules I would use that, for instance, Cartesian rules of geometry. I would know to use the correct rules for Minkowski spacetime, and that will allow me to calculate how long time has elapsed, which is now a kind of a length, a space-time length on my map between 2 relative observers, and I will get the correct answer. But only if I use these different rules.
So then what does, according to general relativity, does objects with mass do to the space-time?
Right, exactly. So Einstein struggled for this completely general theory, not a specific solution like a black hole or an expanding space-time or galaxies make lenses, or those are all solutions. That's why what he did was so enormous. It's an entire paradigm that says over here is matter and energy. I'm going to call that the right-hand side of the equation. Everything on the right-hand side of Einstein's equations is how matter and energy are distributed in space-time. On the left-hand side tells you how space and time deform in response to that matter and energy. And it can be impossible to solve some of those equations. What was so amazing about what Schwarzschild did is he found this very elegant, simple solution within like a month of reading this final formulation. But Einstein didn't go through and try to find all the solutions. He sort of gave it to us, right? He shared this, and then lots of people since have been scrambling to try to, I can predict the curvature of the space-time if I tell you how the matter and energy is laid out. If it's all compact in a spherical system like a sun or even a black hole, I can understand the curves in the space-time around it. I can solve for the shape of the space-time. I can also say, well, what if the universe is full of gas or light and it's all kind of uniform everywhere? And I'll find a different and equally surprising solution, which is that the universe would expand in response to that it's not static, that the distances between galaxies would grow. This was a huge surprise to Einstein. So all of these consequences of his theory, came with revelations. that were not at all obvious when he first wrote down the general theory.
And he was afraid to take the consequences of that theory seriously, which is I mean,
Often.
the theory itself in its scope and grandeur and power is scary, so I can
Mhm.
understand. But then there's, the edges of the theory where it falls apart, the consequences of the theory that are
Mhm.
extreme. It's hard to take seriously.
Mhm.
So you can sort
Yeah.
of empathize.
Yeah, he very much resisted the expansion. So if you think about 1905, when he's writing these sequence of unbelievable papers as a 25-year-old who can't get a job, as a physicist, and he writes all of these remarkable papers on relativity and quantum mechanics. And then even in 1915, 16, he does not know that there are other galaxies out there. This just was not known. People had mused about it. There were these kind of smudges on the sky that people contemplated. What if there are other island universes? Going back to Kant, thought about this. But it wasn't until Hubble, it really wasn't until the late 20s, that it's confirmed that there are other galaxies.
Wow.
Yeah,
And he didn't obviously, there's so much we think of now that he didn't think of. So there's no Big Bang,
right.
static universe.
But these are all connected.
Wow. Yeah. So he's operating on very little information.
Very little information. That's absolutely true. Actually, one of the things I like to point out is the idea of relativity was foisted on people in this kind of cultural way. But there's many ways in which you could call it a theory of absolutism. And the way Einstein got there with so little information is by adhering to certain very strict absolutes, like the absolute limit of the speed of light and the absolute constancy of the speed of light, which was completely bizarre when it was first discovered. Really, that was observed. There were experiments trying to figure out, um, what would the relative speed of light be. It's really only massless particles have this property that they have an absolute speed. And if you think about it, it's incredibly strange.
Yeah, it's really strange.
Incredibly strange.
And then so from a theoretical perspective, he takes that seriously.
He takes it very seriously, and everyone else is trying to come up with models to make it go away,
Yeah.
to make the speed of light be a little bit more reasonable, like everything else in the universe. If I run at a car, two cars coming at each other, they're coming at each other faster than if one of them stops. It's really a basic observation of reality, right? Here, this is saying that if I'm racing at a light beam, and you're standing still relative to the source, will measure the same exact speed of light. Very strange. And he gets to relativity by saying, well, what speed? Speed is distance, it's space over time. It's how far you travel, it's the space you travel in a certain duration of time. And he said, well, I bet something must be wrong then with space and time. So this is an enormous leap. He's willing to give up the absolute character of space and time in favor of keeping the speed of light constant.
How was he able to intuit a world of curved space-time? Like, I think it's like
Yeah.
one of the most
Oh my
special
gosh.
leaps
Yeah.
in human history, right? Because you're
It's amazing.
like, it's very, very, very difficult to make that kind of leap.
I'll tell you, it took me, I think, a long time I can't say this is how he got there exactly. It's not as though I studied the historical accounts or his description of his internal states. This is more having learned the subject, how I try to tell people how to get there in a few short steps. Um, One is to start with the equivalence principle, which he called the happiest thought of his life. And the equivalence principle comes pretty early on in his thinking. And it starts with something like this. Like right now, I think I'm feeling gravity because I'm sitting in this chair and I feel the pressure of the chair and it's stopping me from falling. And lie down in a bed and I feel heavy on the bed. And I think of that as gravity. And Einstein has a beautiful ability to remove all of these extraneous factors, including atoms. So let's imagine instead that you're in an elevator and you feel heavy on your feet because the floor of the elevator is resisting your fall. But I want to remove the elevator. What does the elevator have to do with fundamental properties of gravity? So I cut the cable. Now I'm falling, but the elevator is falling at the same rate as me. So now I'm floating in the elevator. And if this happened to me, if I woke up in this state of falling or floating in the elevator, I might not know if I was in empty space, just floating, or if I was falling around the earth. They're equivalent situations. I would not be able to tell the difference. I'm actually, when I get rid of the elevator in this way by cutting the cable, I'm actually experiencing weightlessness. And that weightlessness is the purest experience of gravity. And so this idea of falling is actually fundamental. It's how we talk about it all the time. The Earth is in a free fall around the sun. It's actually falling. It's not firing engines, right? It's just falling all the time, but it's just cruising so fast.
So actually, yeah, oh God, you said so many profound things there. So one of them is really one of the ways to experience space-time is to be falling.
To be falling. That is the purest experience of gravity. The experience of gravity, unfettered, uninterrupted by atoms, is weightlessness.
Yeah.
That observation, no, it has an unhappy ending, the elevator story,
Yeah.
right? Because of atoms again. That's the fault of the atoms in your body interacting electromagnetically with the crust of the earth or the bottom of the building or whatever it is. But this period of free fall, so the first observation is that is the purest experience of gravity. Now I can convince you that things fall along curved paths because I could take, a pen, and if I throw it, we both know it's going to follow an arc. And it's going to follow an arc until atoms interfere again and it hits the ground. But while it's in free fall, experiencing gravity at its purest, what the Einsteinian description would say is it is following the natural curve in space-time inscribed by the Earth. So the Earth's mass and shape curves the paths in space, and then those curvatures tell you how to fall, the paths along which you should fall when you're falling freely. And so the Earth has found itself on a free fall that happens to be a closed circle, but it's actually falling. The International Space Station uses this principle all the time. They get the space station up there, and then they turn off the engines. Can you imagine how expensive it would be if they had to fuel that thing at all times, right? They turn off the engines. They're just falling.
Yeah, they're falling.
And they're not that far up. There are certainly people sometimes say, oh, they're so far away, they don't feel gravity. Oh, absolutely. If you stopped the space station, it's going like 17,500 miles an hour, something like that. If you were to stop that, it would drop like a stone right to the Earth. So they're in a state of constant free fall. And they're falling along a curved path. And that curved path is a result of curving space-time.
And that particular curved path is calculated in such a way that it curves onto itself, so you're orbiting.
Right. So it has to be cruising at a certain speed. So once you get it at that cruising speed, you turn off the engines.
But yeah, to be able to visualize at the beginning of the 20th century, that free falling in curved space-time. Boy, the human mind is capable of things. I mean, some of that is constructing thought experiments that collide with our understanding of reality. Maybe in the collisions and the contradictions, you try to think of extreme thought experiments that exacerbate that contradiction and see, like, okay, is there another model that can incorporate this? But to be able to do that, I mean, it's kind of inspiring because, there's probably another general relativity out there.
Yeah.
In all, not just in physics, in all lines of work, in all scientific pursuits. There's certain theories where you're like, okay, I just explained like a big elephant in the room here that everybody just kind of didn't even think about.
Right.
Like there could be, for stuff we know about in physics, there could be stuff like that for the origin of life on Earth.
Yeah.
Everyone's like, yeah, okay. Everyone's like in polite companies, like, yeah. Like, somehow it started.
Right.
Nobody knows.
I find it wild that that's so elusive.
Yeah, it's strange. In the lab, you
It's
can't
strange that
replicate.
it's so
I think
elusive.
it's a general relativity thing. There's going to be something. It's going to involve aliens and wormholes and dimensions that we don't quite understand, or some field that's bigger than like. It's possible, maybe not. It's possible that it's a field that is different, that will feel fundamentally different from chemistry and biology. It'll be maybe through physics. Again, maybe the key to the origin of life is in physics. And the same there, it's like a weird neighbor is consciousness. It's like, all right.
A weird neighbor, yeah.
It's like, okay, so we all know that life started on Earth somehow. Nobody knows how. We all know that we're conscious. We have a subjective experience of things. Nobody understands that.
Right.
The people have ideas and so on.
Right.
But it's such a dark sort of, we're entering a dark room where a bunch of people are whispering about like, hey, what's in this room? But nobody has a effing clue. So, and then somebody comes along with a general relativity kind of conception where like reconceives everything. And you're like,
It's like a watershed moment.
Yeah.
Yeah.
Yeah, and it's there, and until
It's there.
we're living in we're living in a time until that theory comes along, and it'll be obvious in retrospect.
Yeah.
But right now we're
Right. Well, it was obvious to no one that space-time was curved, but even Newton understood something wasn't right. So he knew there was something missing, and I think that's always fascinating when we're in a situation where we're pressure testing our own ideas. He did something remarkable, Newton did, with his theory of gravity, just understanding that the same phenomenon was at work with the Earth around the sun as the apple falling from the tree. That's insane. That's a huge leap. Understanding that mass, inertial mass, what makes something hard to push around, is the same thing that feels gravity, at least in the Newtonian picture, in that simple way. Unbelievable leap. Absolutely genius. But he didn't like that the apple fell from the tree even though the Earth wasn't touching it.
Yeah, the action at a distance thing.
The action at a distance thing.
That is weird too.
Well, but
that is a really weird one.
It's really weird. But see, Einstein solves that. Relativity solves that. Because it says the Earth created the curve in space. The apple wants to fall freely along it. The problem is the tree's in the way. And the tree's the problem. The tree's actually accelerating the apple. It's keeping it away from its natural state of weightlessness in a gravitational field. And as soon as the tree lets go of it, the apple will simply fall along the curve that exists.
I would love it if somebody went back to Newton's time
and told him all this.
Probably some hippie would be like, it's a gravity is just the curvature in space time, man. I wonder if he would be able to. I don't think there's every idea has its time. He might not even be able to load that in. I mean that sometimes even the greatest geniuses, I mean, you can't.
Like you need too out of context.
You need to be standing on the shoulders of giants and on the shoulders of those giants and so on.
I heard that Newton used that as an unkind remark to his competitor Hooke.
Oh no. The people talk shit even back then.
Yeah, trash talking.
That's one of the hilarious things about humans in general, but scientists too. Like these huge minds. There's these moments in history where you'll see this in universities, but everywhere else too. Like you have gigantic minds, obviously, also coupled with everybody has an ego, and like sometimes it's just the same soap opera that played out amongst humans everywhere else. And so you're thinking about the biggest cosmological objects and forces and ideas, and you're still like jealous and
right. I know.
Your office is bigger than my office.
I know.
This chair, this or maybe you got married to this person that I was always in love with. There's a betrayal or something.
Right. The one woman in the department.
The one woman in the department. Yeah. And it's just, I mean, but that is also the fuel of innovation, that jealousy, that tension. That's
well, the expression, nature. I'm sure the battles are so bitter in academia because the stakes are so low.
That's a beautiful way to phrase it. But also, like, we shouldn't forget, I mean, that I love seeing that even in academia because it's humanity.
Mhm.
The silliness, there's a degree to academia where the reason you're able to think about some of these grand ideas is because you still allow yourself to be childlike.
Oh, yeah.
There's a childlike
Oh,
nature to
there's
be
no
ask the big
question.
questions,
Oh,
but
yeah.
children can also be like
Children.
children. So like, you don't I think when, in a corporate context and maybe the world
Mhm,
forces you to behave, you're supposed to be a certain kind of way.
mhm.
There's some aspects, and it's a really beautiful aspect to preserve and to celebrate in academia is, like, you're just allowed to be childlike in your
Yeah.
curiosity and your exploration. You're just exploring, asking the biggest questions, so
Mhm. The best scientists I know often ask the simplest questions. They're really first of all, there's probably some confidence there, but also they're never going to lie to themselves that they understand something that they don't understand. So even this idea that Newton didn't understand the apple falling from the tree, had he lived another couple hundred of years, he would have invented relativity because he never would have lied to himself that he understood it. He would have kept asking this very simple question. I think that there is this childlike beauty to that. Absolutely.
yeah, just some of the topics. I don't know why I'm stuck to those two topics of origin of life and consciousness, but there's
I'll talk about those.
some of the most brilliant people I know
Mhm.
are stuck, like, just like with Newton and Einstein. They're stuck on that. This doesn't make sense. I know a bunch of brilliant biologists, physicists, chemists that are thinking about the origin of life. They're like, this doesn't. I know how evolution works. I know how the biological systems work, how genetic information propagates, but like this part, the singularity at the beginning doesn't make sense.
Mhm.
We don't understand. We can't create it in a lab. They're bothered every single day. They're bothered by it, and that being bothered by that tension, by that gap in knowledge is, yeah, that's the catalyst. That's the
That's the
fuel
catalyst.
for the
Mhm.
for the
Discovery.
for discovery.
Yeah, absolutely. The discovery is going to come because somebody couldn't sleep at night.